As the world progresses, there is a growing focus on sustainability to minimize environmental harm. Global issues such as global warming, climate change, biodiversity loss, and the increase in greenhouse gases have intensified the urgency for sustainable solutions. The construction and operation of buildings contribute significantly to these issues, accounting for a substantial portion of global energy consumption and emissions. Additionally, traditional energy sources like coal, oil, and natural gas release large quantities of greenhouse gases and other pollutants when burned for electricity and heating. This accelerates climate change and affects ecosystem. Consequently, the development of low-energy and net-zero buildings is critical in mitigating these impacts. These buildings aim to reduce energy consumption and minimize greenhouse gas emissions and other pollutants. Energy efficiency is a key aspect of this focus, leading to the rise of low-energy and net-zero buildings that incorporate strategies that significantly reduce energy demand. The Vodafone Site Solution Innovation Center in Midrand, designed by GLH Architects, completed in 2011, is an exemplary model of such sustainable architecture. The building responds to these issues through its innovative use of daylighting, renewable energy sources, efficient water management system, and advanced HVAC technologies, all of which collectively reduce its environmental footprint. Located in Midrand, South Africa, the Vodafone Site Solution Innovation Center faces a subtropical highland climate characterized by warm, wet summers and cool, dry winters. Daylighting and facade design. The facade combines functionality and aesthetics. Large double-glazed windows allow natural light while minimizing heat gain. Fixed white louvers with mirrored finishes reduce glare and extend light up to 5 meters from the facade, reaching 2 meters into the corridors. This design ensures 90% of the building area benefits from daylight while minimizing heat entry. The daylight responsive artificial lighting system maintains an 8 watts per meter squared lighting load with illumination between 250 and 300 lux, aligning with South African energy efficiency standards. Dynamic blind system. Blinds are adjusted throughout the day to optimize light transmittance and reduce glare and heat gain. In the morning, blinds allow maximum light, reducing the need for artificial lighting. By midday, they minimize glare and heat gain. And in the evening, they balance natural and artificial light. Water efficiency. An innovative rainwater collection system combined with a grey water system and energy-efficient water fittings is utilized for irrigation and toilet flushing, reducing potable water usage by about 65% and saving over 818 cubic meters annually. Additionally, grey water from showers, basins, and taps is treated through a septic tank and then directed to a mini on-site wetland with a reed bed planting system via a subsoil soaker hose. Microorganisms on the reed roots cleanse the grey water before it is released. The treated water is stored for over 24 hours, with any excess directed to the campus's sewage system. Renewable energy. Vodafone Site Solution Innovation Center features a 55 kilowatt photovoltaic installation on the roof and walkways, with an expected output of 92,467 kilowatt-hour per annum. Slimline solar film cells are used as an alternative to traditional solar panels, particularly for base station in urban areas with limited space. These cells offer a smaller ecological impact compared to crystalline silicon cells, enhancing the sustainability of the installations. HVAC system and gabion rock stores. The most interesting aspect of the building would be the HVAC systems found within. These rock stores serve both a structural purpose and play a crucial role in passive cooling. Air is carried through gaps between the gabion rocks through air pullers, where it cools down before entering the office spaces. While the exact rock type used in the gabion walls of the Vodafone Site Solution Innovation Center in Midrand is unknown, the rock types used in gabion walls tend to be limited to these 5 types: granite, limestone, basalt, sandstone, and river rocks, all of which contributes to cooling effects of the gabion rock store. Porous rocks like limestone and sandstone retain more water, enhancing evaporative cooling as air passes through. Dense rocks such as granite and basalt with high thermal mass absorb and slowly release heat, stabilizing temperatures and maintaining cooler airflow. They exhibit a notable cooling effect through three main mechanisms. Firstly, as air flows through the interstitial spaces of the rocks, any trapped moisture evaporates, a process known as evaporative cooling. This evaporation absorbs heat from the surrounding air, effectively lowering its temperature. Secondly, gabion rocks possess a high thermal mass, enabling them to absorb and store significant amounts of heat. During the day, warmer air passing through the rocks transfers some of its heat to the cooler rocks, resulting in the cooling of the air. This thermal mass effect is particularly pronounced when the rocks have cooled overnight or are shaded from direct sunlight, as they are in the case of the Vodafone building. Additionally, direct heat exchange occurs between the warmer air and the cooler rock surfaces, with heat transferring from the air to the rocks through conduction. Active cooling system. The active cooling system uses solar absorption cooling. Thermal solar panels generate hot water directed through vessels and an absorption chiller that uses lithium bromide as the refrigerant. This chiller has zero ozone depletion potential (ODP) and zero greenhouse warming potential. The cooled water flows beneath thermally activated slabs and into radiant panels, providing efficient radiant cooling to floors, walls, and ceilings. In addition to this system, the water cycle for cooling incorporates the reuse of grey water for flushing and irrigation, as well as the harvesting of rainwater. The collected rainwater from the rainwater harvesting system is used to cool the slabs, with a pipe network beneath the slabs, transporting the cool water and providing radiant cooling from the bottom. But with all these innovations, can it be said that the systems are effective in achieving their intended goals? A journal article by Vumbe and Inambao from the Department of Mechanical Engineering at the University of KwaZulu-Natal in South Africa studied the performance of the autonomous solar-powered absorption air conditioning system at the Vodacom Site Solution Center. The study found that the solar cooling system successfully maintained the building's temperature within the desired limits throughout the day. The average building temperature was 22.57 degrees Celsius, with a maximum of 24.9 degrees Celsius and a minimum of 20.4 degrees Celsius. The humidity levels averaged 57.6%, ranging from a high 61.16% to a low 53.3%. Based on the psychometric charts of Midrand, the comfortable temperature zone is between 20 degrees Celsius and 27 degrees Celsius, indicating that the building's temperature consistently remains within the thermal comfort zone. In terms of energy efficiency, the creation of wide pergolas along the eastern and western sides of the building increased the roof area, allowing for the installation of 292 photovoltaic panels. These panels deliver 230 kilowatt-hour of solar energy, which is double the building's energy requirements. The surplus energy is fed back to the Vodacom campus, effectively creating a zero-energy building. In conclusion, the Vodafone Site Solution Innovation Center stands as a beacon of sustainable architecture, showcasing how innovative design and technology can create buildings that are both environmentally friendly and highly efficient. Through its integration of renewable energy sources, advanced HVAC systems, and water efficiency measures, the center not only reduces its environmental footprint but also sets a new standard for sustainable building practices. By achieving a zero-energy status, the center demonstrates the feasibility and benefits of low-energy and net-zero buildings in mitigating environmental impacts, serving as an inspiring example of what can be achieved when sustainability is prioritized in building design and construction.